we're going to have our presentation from our friend and collaborator, Randi Dodgson. Randi's a PhD candidate in Michigan Tech, and she's going to be talking to us about the research that she and her colleagues there are doing on structural grading and engineered wood applications of underused wood species. And, this is so exciting. And obviously, we've been following this work and speaking with Tech about their work for years, and they're starting to have some really I think even surprisingly promising results with some of these Michigan species that don't have really valuable markets right now for a variety of reasons that Randi's going to discuss. And I know, again, this is an issue that many people on this call care about, whether you're working in forestry or natural resources, whether you're in the wood products industry. And I know that many architects and engineers and developers and people who are working on the construction side of things are always asking, when can we use more Michigan species? Will we be able to use hardwoods? How long is this going to take? So Randi's she doesn't have all of the answers to all of those questions, but she knows a lot about the how promising some of these species really are. So with that, Randi, I'm going to stop sharing my screen and welcome you to make your presentation to the Michigan Mass Timber Community of Practice. We're super happy that you're here.
Hi, everyone. My name is Randi Dodgson. As Sandra mentioned, I'm a PhD student. I just finished my qualifying exam, so paperwork pending, PhD candidate here soon. My working dissertation title is Structural Grading and Engineering Applications of, should I get this out of the way? Can you see this, or is this um, uh, underutilized wood species? I'm at in the forestry building up in Houghton, Michigan at Michigan Tech. I do work, my dissertation work is in both softwoods and hardwoods, but today I want to talk to you about hardwoods in particular, um, and kind of the technical barriers and perhaps emerging opportunities that we're seeing with hardwood mass timber right now. I should also mention, I prefer to have like kind of more of an open discussion. So maybe at the end of like every couple of slides, I'll open it up for discussion instead of waiting until the end too. Um, so as architects, engineers, contractors, or if you're part of this meeting, right, you may have specified mass timber for a project. So you might be wondering if Michigan has so many hardwoods, can mass timber be made from Michigan hardwoods? And the answer is technically yes, but in practice, the answer is much more complicated. Um, Michigan has nearly 20 million acres of forest land, and much of that resource is hardwood. Maple, beech, birch is the state's largest forest type, and sugar maple and red maple alone make up about 30% of Michigan's sound wood volume. So Michigan has no shortage of wood. What we have here is a mismatch between the species growing in our forests and the species around which most of the structural lumber standards, manufacturing systems, and engineered wood products were developed. And this is why we do not yet see hardwood mass timber being widely manufactured or specified. Um, Expanding hardwood use requires more than just demonstrating that the material is strong enough. We know it's strong enough. It requires systematic changes to the grading systems, the way hardwood lumber is processed, testing, maybe reevaluating published design values, going through the route of product certification, and then ultimately market acceptance after softwoods have dominated this market. Um, the entire time, really. So before we examine these barriers, I want to kind of back up and clarify what we actually mean when we're talking about hardwood versus softwood, because the distinction is more complicated than the name suggests. Um, Even industry people might loop a hardwood in with a softwood like a poplar. And yeah, so the names are a bit of a misnomer, hardwood and softwood, right? These are actually botanical classifications and they're not direct measures of hardness or strength. So hardwoods come from angiosperms or flowering plants, and their seeds are enclosed within a fruit. and they typically have broadleaves. Most temperate hardwoods are deciduous, although there are some exceptions. There are some exceptions to all of these kind of generalizations here, right? Um, so hardwoods here, we have a maple tree. The flower here would be a birch catkin, and then these are white oak leaves. So hardwoods are trees with leaves. And like I said, there's even some back and forth on that if you talk to harvesters and stuff. But whereas softwoods are gymnosperms, which generally produce cones and they have exposed seeds. They commonly have needles or scales, and they are often evergreen, though there are some species like tamarack, right, that the needles turn orange and fall off in the winter. Um, these two plant groups, angiosperms and gymnosperms, actually have like very different evolutionary histories. Gymnosperms appeared up to 20 or 200 million years before angiosperms did, in the world since the beginning of the world. And um, angiosperms did not necessarily develop from gymnosperms. So we're actually talking about two very different things. I like to tell students sometimes it's like not comparing like a trout to a salmon. It's like comparing a trout to a dog or something like that. And I don't know if that's actually true, but I like to use these analogies with students. Um, the most important difference for wood products is the internal anatomy. Hardwood structure is relatively newer, right? And so it's definitely more complex. The cell types are much different. We've got vessels, fibers, and other like specialized cell types. Um, and then this creates considerable variation among hardwood species and produces different porosity patterns and ultimately affects how the wood moves and some of the mechanical properties of the wood. Um, whereas softwoods have a much simpler and more uniform structure, and it's dominated by tracheid cell types. Um, and to illustrate this, I've included some images on the left here from the Wood Handbook. Uh, I outlined in the middle section there commercially relevant species in the northern area, and on the left, I've included some species on the top left there. We have white ash, uh, quaking aspen, American beech, elm, sugar maple, and red oak. And these are all at 15 times magnification. So if you're looking at the end grain of a board, so like the board is going in and out of the screen from you, this would be, yeah, 15 times magnification of that end grain. On the right, however, um, we have our softwood species. At the top is balsam fir, eastern hemlock, eastern white pine, red pine, white spruce, and white cedar. So you can see that these are definitely much easier to group into species. They can be difficult to differentiate, species to species. They're very similar and they're very uniform. Um, then to the right, I've included some generalizations. Again, generalization is the key word here. From the design values of the NDS and Wood Handbook. When we're talking about density, we measure wood density in specific gravity. And typically, hardwoods have a higher density, and generally, softwoods have a lower density. Again, there's exceptions to this rule. Um, the MOE is the modulus of elasticity. This is a measurement of strength. Sorry, stiffness, not strength. And um, we see a moderate to high MOE and a moderate MOE in softwoods. However, species and grade might matter for this category more than the softwood hardwood distinction. MOR represents the strength, especially the bending strength under short duration loading. Uh, Hardwoods generally have a higher MOR. When we're talking about compression parallel to the grain, we have a high value versus a moderate value in the softwoods. And you can kind of see this pattern emerge. We have compression perpendicular, tension parallel to grain, shear, allowable shear is typically higher. In hardwoods, the hardness is a measurement We use the Jenga scale, and hardwoods are generally tougher and harder. Um, the fastener withdrawal resistance is particularly higher in hardwoods. One of maybe the downsides of using hardwood is because it is generally denser. We get a good strength to weight ratio, but is heavier, which can cause issues when we're talking about transporting the material around. So before we get into kind of more of the history, is there any questions I can answer about wood anatomy?
And I would invite people to just feel free to unmute and ask the question.
Mhm.
Seems like there are no questions about wood anatomy.
Okay, I could go on and on about this, but I won't make you do that. Um, So I guess the key point I'm trying to make here is not that hardwoods lack adequate mechanical properties. It's, in many cases, they even compare very favorably. The more important question is maybe why structural lumber and mass timber systems became centered around softwoods in the first place. And to answer that, I wanted to take a look back at kind of the history of um, wood products in our state and the development of standardized wood products and the development of grading systems really over the past 200 years. Um, so going way back, right? I think it's important to talk about the landscape prior to Euro-American settlement. Michigan supported a much more diverse forest type than we see today. It was shaped by natural disturbance and generations of indigenous stewardship. Southern Michigan was dominated by oak, maple, beech, while northern forests included a mix of sugar maple, beech, birch, hemlock, white pine, cedar. So I guess the point I'm trying to make is that these were not untouched forests, as one might believe, I guess, but they were cultural landscapes and they were managed for food, materials, habitat, and other community needs. Um, Early Euro-American settlement reshaped Michigan's forests as the land was cleared for farms, roads, towns, and local sawmills. At this point in our state's history, the timber was generally treated more as an obstacle to settlement than a source of immediate building material or fuel. However, once timber was no longer harvested only for local settlement needs, attention shifted um, toward the species that could be cut, transported, and processed most efficiently at an industrial scale. And in Michigan, that species was eastern white pine. Um, and this is the lumber boom, and probably like the most exciting time in Michigan forestry. So during this white pine lumber boom, so-called shanty boys poured into the forests and they cut down the majority of large diameter pine logs through the winter and they sent them downstream with the spring thaw.
Think about it. When you have
Um,
350 years.
Rivers became industrial highways and they carried timber to booming sawmill towns like mild stomping grounds in Grayling, Saginaw, and Muskegon. Um, and this is when and where lumber barons built huge fortunes and Michigan wood helped to grow the Midwest. However, by the 20th century, much of the original white pine resource was gone. Cutover lands, which were kind of abandoned agricultural swaths, um, fires, and abandoned agricultural areas reshaped the landscape and Michigan's forests eventually return, but the forests that were regenerated are very different than they were before, with hardwoods becoming a much larger part of the resource that we have today. So as Michigan's hardwood industry expanded, it developed around regional strengths or regional species rather than standardized structural products. Grand Rapids became internationally known for furniture, while northern Michigan and the Upper Peninsula supported flooring, millwork, veneer, pallets, industrial lumber, sawmilling, pulp, and paper markets. And these clusters, these manufacturing clusters, grew where timber, transportation, labor, suppliers, and markets kind of all came together. And over time, they kind of reinforced their own specialized expertise. And that specialization also shaped how hardwoods were valued. Um, they were more valued for appearance, like color, grain, hardness, how easily they were able to be machined or shaped into components, parts or components. Um, and ultimately, like the recovery of the clear material, the clear wood fiber, mattered more than the full length structural performance of a board. Um, Random width and random length lumber made sense for these types of industries, in particular, furniture parts, flooring, and cabinetry. Meanwhile, the softwood industry was building an entirely different system based on standardized dimensions, structural grades, design values, predictable performance. So as Michigan's forest became increasingly hardwood dominated, the industry could not simply substitute hardwoods for softwoods. A sophisticated Michigan had developed a sophisticated hardwood economy, but not one designed to produce structural lumber. Um, so I'm probably missing a few things in here, but again, kind of a general timeline I wanted to point to, and the way in which structural grading standards were developed. So in the late 1800s, early 1900s, we had very regional and mill specific grading rules, and the lumber was commonly graded according to its ultimate end goal or local trade expertise. Um, Grade names, dimensions, quality expectations varied between regions and species, and early structural decisions relied heavily on experience and visual inspection. Um, into the 20s, the National Softwood Standardization began. It's almost 100 years ago now, which is wild. The industry efforts to standardize lumber began, and the first American lumber standard was published in 1924. And it established a national framework for lumber sizes, grades, inspection, grade marking, and an early assignment of design values. In 1933, NELMA was established. NELMA is Northeastern Lumber Manufacturers Association, and was developed primarily for grading eastern white pine and other softwoods. Although they're the ones who, I don't want to use the word own hardwood design values, but they're the ones, I'm not sure if I'm wording this right. They're the ones who publish the hardwood design values currently, and like the NDS. Speaking of the NDS, the first NDS was published in 1944. I'm sure many of you have used this document to specify material. In the 50s and 60s, engineered wood standards expanded into plywood, glulam. Yeah, and these standards started to grow. A lot of product testing, in particular, southern yellow pine and Doug fir was tested at this time and really defined. In the 70s, we have the National Grading Rule for Dimension Lumber, and it's now administered through American Softwood Lumber Standard. In the 80s and 90s, we saw a shift toward in-grade testing. And this was kind of ultimately the shift to stress grading MSR sawmill implementation to do non-destructive testing. The IBC was adopted in 2000. I think this was like the earliest one I could find, but it's an important part of specifying materials for mass timber jobs. And then As we continue, you can see more certification, qualification standards develop. And again, this is really a short timeline of all the things. Meanwhile, the U.S. hardwood industry developed around appearance-based products rather than structural construction. Hardwood grading systems were developed to measure clear cutting yield for furniture cabinets, etc. And these markets expanded increasingly into the 1990s. And in 1999, we saw the peak of the US hardwood lumber industry. However, the hardwood grade lumber consumption fell from 7.7 billion board feet in 1999 to 2.7 billion board feet in 2009. And this is a 65,000 or 65% decline. And a lot of it has to do with a lot of furniture manufacturing and domestic furniture manufacturing moving overseas and domestic production declining for furniture, flooring, and most of the hardwood product industry. Today, the United States still has a substantial hardwood resource, but limited structural grading, manufacturing, and certification pathways continue to restrict the use in modern engineered wood products. And this point is illustrated by Dallin Brooks. He's CFO, CEO of NHLA, National Hardwood Lumber Association. And he said, we must embrace structural grades for hardwoods because hardwoods are stronger than softwoods. Our one common ground should be in structural and appearance-based grading. So what are we doing about it? Research I've included, there's more than this out there, but I kind of wanted to be a little bit concise and not bore anyone with scientific literature. But research on hardwood cross-laminated timber has demonstrated that low-value hardwood lumber can provide both a viable structural material as well as potential higher value market for regional forest resources. Probably the most well-known North American research is out of Virginia Tech. And this is basically the path, the research that yellow poplar took to become certified and a material in the PRG 320. More recently, this team has moved their yellow poplar CLT production out of a laboratory and then into a commercial manufacturing facility. So the significance of this is that they're testing full-size panels. So you can see how hardwood behaves under varied loading conditions. Kentucky explored some, University of Kentucky rather, some underutilized species, red maple, sycamore, and sweet gum. And this testing was done on the compression properties relevant to wall and bearing applications. And this work was significant because it went beyond like the laboratory testing of small scale samples, bending samples, and into additional structural loading conditions that would be relevant in large buildings. Here at Michigan Tech, I'm more familiar with this research. Yunsham Ma, my colleague, demonstrated that low-value sugar maple CLT could provide approximately 50 to 80% greater stiffness and at least twice the bending strength of the PRG 320 E1 reference layup. He also showed that non-destructive lamination grading and strategic placing of the higher stiffness boards in the outer layers or the strong axis, if you will, and that could improve the panel performance. Then additionally, he evaluated whether he could use this low-grade sugar maple, again in the strong axis, combined with white spruce in the minor axis to manufacture what we call hybrid panels now, mixing hardwood and softwood species. This is significant because it would make the panels weigh less when you aren't using hardwoods in the center layers. After this, Monkaila Musa tested 45 species combinations using MUR and PRF adhesives And the um, the hardwoods I outlined here were mixed with red pine and white pine. And these combinations, the hardwood combinations generally produced a higher shear strength, but wood failure performance depended on species anatomy and adhesive. Um, so this work has extended through hybrid sugar maple and white spruce panels, and Musa's bonding research across several Great Lakes hardwoods. And these studies have shown that hardwood is most structurally effective when placed in the longitudinal outer layers or the strong axis, like I said, while also demonstrating that bonding performance varies substantially among different species. And I said I was going to take breaks and ask questions, but I've just been talking this whole time. Is there any questions I can answer?
If you have a question for Randy right now, feel free to unmute.
So I got a question.
What's that?
The adhesives, is that due to the porosity of the wood or?
It is. It is quite a bit. In particular, when we're looking at red oak, I have some red oak finger joints right here. As you know, the pores in red oaks are huge, right? And we found that if the viscosity of the adhesive is not considered, that the pores will actually starve. They'll pull the adhesive right out of that glue joint. There's also some general discussion about the alignment of the growth rings and the glue line. But again, the hardwood anatomy varies significantly. So there's going to need to be additional research into which adhesive performs the best for which species and, processing conditions.
Thanks for the question, Bill.
Any other ones? I also wanted to give a shout out to Dr. Mark Rudnicki. He and his students have gone beyond laboratory testing, and they've started to construct demonstration projects using red maple CLT. And this is great because it is good for public to see the potential of these regional hardwoods in these real world applications. What's really great about these are 3-ply CLT, and each lamination is about 3/4 of an inch, so you get much thinner material, and it's strong, it's beautiful, it's maple, and so I love these proof of concepts work that he's doing, and I think they really highlight the gap between successful demonstrations, but we still need commercial adoption, right? So he and a student brought this down to the Michigan Forest Products Show in Gaylord in 2024. And the kiosk demonstration on the right is at the Newberry Visitor Center there. So you might be wondering if we've identified in research that hardwood can meet or potentially exceed existing design parameters. What's stopping hardwood from being adopted into these mass timber supply chain? And the issue is how the wood is processed. On the left, I've included an image of a hardwood log versus like a typical cut sheet for a softwood mill. So in a hardwood mill, the logs are brought in. They're all different size diameters. And a sawyer is going to be removing these jacket boards first. These are the highest value boards. And this whole time, spinning the board and taking a cut. Yep, and the material is then it's going to be random width and it's going to be random length, and typically 4/4 in thickness, which is about an inch and 13/16 after it's been surfaced two sides. So we have thinner material. They're really not set up in any way to like a softwood mill here, right? These are log diameter sizes. In a softwood mill, they'll set up their saws to mill boards at a certain size for one day. So logs are coming through the mill and they're shooting through these gang saws really, and they're producing this dimensional stock. They're not trying to get as much of the clear wood out of the board as possible. They're going for quantity. Any questions about this? I guess I have another point down here on the bottom too. Hardwoods and softwoods are dried differently. Because of the original applications for hardwoods, we've always dried hardwoods to about 6 to 9%, which can be very energy heavy, especially removing moisture in those last couple of percentages. So what we've found is that by removing moisture down to this level, when you then go and make furniture parts out of it, you don't necessarily have to worry about the wood movement. Whereas softwood, depending on its ultimate end goal, is dried to 12, 16, 19%. 19% would be the fiber saturation point, where I don't need to get into that. But what we found is that if we, let's say, make a red oak glulam at 6% moisture content, once it's installed in a place, typically we experience in softwoods, the material shrinks as it settles into its new place. But hardwoods tend to grow because it's absorbing moisture back in from the air and its environment. So there's some considerations that need to be made for the moisture content of the wood as it's being processed or manufactured into maybe an engineered wood product. Any questions?
I say keep going.
Okay.
It's so interesting, Randy. Thank you.
Mm-hmm. Mechanical properties need to be proven. They should not be assumed. These plots over here on the right are from a recent study I did. I do a lot of work with non-destructive evaluation. If we were to implement an MSR system into a hardwood mill, we want to know if we're getting accurate readings and how the softwood visual grading systems that are in place, how they relate to the hardwood material. So this is from some sugar maple boards, 171 sugar maple boards. I wanted to know if an MSR piece of equipment was implemented at a hardwood mill, how would the readings change over frozen, green, and kiln-dried conditions, right? Because a lot of the hardwood work has been done only in laboratory settings when the wood has been dried and then reconditioned to 12%, which is what the standard requires. So I wanted to know if there was a visual grading system that was a good indicator of the stiffness performance. So on the top here, again, I graded all of these boards, 171 boards, in NELMA on the top here, and then NHLA on the bottom. And this R squared value is the proportion of the dynamic E variability that's explained by the visual grading system. And you can see that these numbers are very low. And so neither visual grading system that are in place for red maple are good indicators of the grade as the stiffness value explained. And you can see here that in some of these grades, we were getting really high stiffness values, and this was all cant lumber stock, so really low grade material. So you have any questions about this research? I just published a paper on this.
Did you already define cant lumber stock? I don't remember if I heard you say that word today or just yesterday in our conversation.
Sure. So in a hardwood mill, cants would be like the byproduct of this high yield board, right? So the sawyer is going to be going around and getting these jacket boards, removing these jacket boards, and what's left here is this square cant in the middle. And sometimes some hardwood mills send this to go to rail tie market. And sometimes, like in this case, it looks like it was sent through a gang saw. And these would be like a similar setup to this type of scenario where they have just um, a set of circular saws that are evenly spaced to just rip right through those cans. And this is the lowest value product from the board. Um, yeah, so that would be canned stock there. So yeah, this is red maple, and you can see that excuse me, this is sugar maple. We achieved some really good design values, and this is a smaller project of the bigger 2024 Wood Innovations funding that we received to look at MSR for red maple. Any other questions here? Another issue to hardwood adoption would be the manufacturing of these hardwood products, and in particular, talking about the value adding. Um, this the first half of my dissertation is on MSR for hardwoods. The second half is really on value adding and um, developing the optimal conditions for these structural finger joints. Currently, the standard for structural finger joints is based around softwood products. And when we add this finger joint profile and the other adhesive requirements and so on from the standard, we don't get the strength we want. And so we've been trying to evaluate different finger joint profile geometries, adhesive press times, press pressure, etc. And so I've broken so many thousands of these red oak and sugar maple, red maple boards. The issue really here is that hardwood logs are typically cut to 100 inches in length. If you've seen a logging truck driving down the road, um, hardwood logs are typically stacked perpendicular to the truck bed, whereas softwood logs are tracked parallel. And it really is just how the hardwood mills process the logs. But in this case, we're really just limited to 8-foot long pieces if we can't identify a strong enough finger joint for glulam especially, but also CLT. A problem here is that the higher density hardwoods can be more difficult than softwoods to machine and press. And then we have the anatomical nature of the hardwoods varies so much that there might be differing parameters for different species or porosities. Maybe they can be grouped, but some more testing needs to be done. Yeah, so that's what I'm working on here. Does anyone have any questions about this? And then kind of just some last points here about some barriers to hardwood adoption would be the need for product qualification and testing, and it can't just be done in a laboratory setting. We need full-scale products that demonstrate bending, shear, bond, durability, dimensional performance, as I mentioned with hardwoods. And we also need to start looking at the layup configurations. Are we going to put hardwoods on the outside of CLTs only and keep softwoods in the center? Are there species combinations that we can make that would ease this into standardization? And how do adhesive systems affect these results, especially durability? And then, we have market adoption. Softwoods have dominated this industry for 100 years. it wouldn't be an easy thing for a hardwood mill to completely change their infrastructure to start manufacturing dimensional lumber. It's doable, but there's cost for equipment, testing, certification, quality control. And then on the other hand, designers, engineers need maybe more reliable properties in published design values. Contractors need predictable products. There's no connections right now. Fasteners that are made for hardwood CLT panels, and so we need to look at that as well. Yeah, building officials, and insurers, they prefer recognized systems. They know softwoods. How do we break in and prove that hardwoods can be a viable contender in this market? And we need to make sure that if we do prove that hardwood would be suitable in this application, how can we make sure that the supply is reliable and to justify the long-term investment? Before I end my speech here, I just wanted to kind of call out some benefits of hardwood mass timber products. Of course, we know in Michigan, we're 70% hardwood in our state, up to 70%. Hardwood mass timber offers a unique opportunity to utilize this abundant regional hardwood resource while also creating higher value markets for lumber that's considered underutilized. Mechanically, hardwoods can provide excellent stiffness and strength, which makes them attractive for structural applications and hybrid mass timber systems. However, beyond engineering, hardwood mass timber supports rural economies, encourages regional manufacturing, stores carbon, offers the natural beauty and biophilic qualities that have made mass timber increasingly popular in modern buildings. And I know there's not really a way to scientifically quantify the aesthetics of hardwood, but I personally believe that they're beautiful. They have a lot of natural characteristic that differs from plantation grown Doug fir or southern yellow pine. And so it'd be really nice to start seeing some different wood profiles, characteristics. These are some of the references I mentioned in the research that's ongoing. And this is my contact information. Does anyone have any questions for me now?
Let's pause just for a moment. I want to thank you, Randi, for your presentation. And I think that there have been so many fascinating points, and I learned so many new things just now, even though I've already spoken with you about this and continue to learn. So thank you so much for your presentation. That was Randi Dodgson with Michigan Technological University presenting on value-added uses for underused Michigan and Great Lakes species in mass timber.